Hi, my name is Sanjana Kedia.
And I'm Emily Ma, and we will be discussing our novel design and prototype which efficiently cleans wastewater.
The inspiration behind this project was an occurrence during a trip to India I took when I was much younger. I remember standing in my grandma's kitchen about to take tap water to drink, but I was quickly stopped and given bottled water instead. This confused me at the time, but my grandma explained the tap water was not clean enough and it could get me sick.
In the past, I've experienced similar circumstances to Sanjana, where the only type of water I've been allowed to drink in China was bottled water due to the fact that tap wasn't safe for consumption.
Emily and I became determined to contribute towards solving the water crisis.
While researching wastewater treatment in the US, we realized that individuals were large contributors to the generation of wastewater. Its cleaning results in high electricity costs, efficiency issues, and pollutant buildup in treatment plants.
We designed a Microbial Fuel Cell system, or MFC, followed by an Algae Bioreactor to remove contaminants from wastewater while simultaneously producing electricity. The novel MFC was constructed using a dual-chambered system separated by a commercially available Nafion membrane. Coli K-12 was used for the transfer of electrons.
The Nafion membrane used in our prototype helped to clean the wastewater by filtering out particulates while also aiding in the movement of hydrogen ions in order to produce electricity and pure water. We also monitored the microbial fuel cell for a 90% increase in dissolved oxygen, which was an indicator that the remediated wastewater had become clean enough for life to survive in it. Lastly, we also measured the power output, current, and voltage in order to calculate the energy efficiency.
The second part of our prototype implemented an algae bioreactor, which essentially involved algae in a water bottle. The partially cleaned wastewater from the MFC was now mixed with the algae to further remove the nitrate pollutants. The nitrates, if left untreated, would cause the water to be too nutrient-rich to sustain life. The nitrates were broken down by the algae into ammonium, which effectively reduced the pollutant levels.
We compared our novel design to a control group and aeration system, which mimicked current wastewater treatment practices, and it was found that our design was the most efficient. We also observed that the MFC was the most time efficient. It increased its dissolved oxygen levels by 90% in just 22 hours, whereas both the control and aeration reactors each took a few days.
The MFC was also more electrically efficient, as it generated more electricity than it consumed during part of the process, resulting in an overall 35% higher efficiency than the aeration system. Saving this electricity is equivalent to saving over 30,000 pounds of carbon dioxide being emitted for each of over 500 individual homes.
Our design was also cost-effective, as the setup for it was less expensive than that of the aeration system. Finally, we observed that the algae bioreactor was capable of significantly removing nitrates from the wastewater, which complied with the nitrate standards for the survival of aquatic life.
We applied for and have a patent pending on our device, as our design was scalable, practical, cost-effective, and showed capability of being used in the real world. We truly believe wastewater treatment will benefit from a device such as ours, as the burden on fossil fuels will be reduced, electricity consumption will be reduced, and the time to treat wastewater will be reduced. Here's to a better tomorrow.